a couple more terms that I want to add to what we've been talking about in the past few videos. So I originally made those sets videos just to get you started on propositional logic. And now I want to kind of go back and introduce a few more things that come up a lot more when we're talking about sets, and that will come up a lot in this chapter. So one is a terminology issue. So if we have not A, we know that the tilde always signifies not. Another way that we can write that in sets is a complement. So if we're talking about a complement, in this case, we're talking about everything that is not A, right? So if we use not A or a complement, those are the same. Another piece of terminology that I want you to be familiar with is minus. So A minus B, it's pretty intuitive. It refers to everything that is in A that is not in B, right? So what I've highlighted here in yellow, which is the same as saying A and union, B complement, or not B. So everything that is in A and at the same time not in B. Which leads us to what we call the symmetric difference, or as you more commonly know it, XOR. So if I have A XOR B, that means A minus B or union B minus A. So let's think about that, right? A minus B, we've already established, is that segment right there. It is in A, but it is not in B. B minus A, similarly, will be everything that's in B, but is not in A. So if it is in A minus B or B minus A, this is what it looks like in a Venn diagram. But remember, as we just did an equivalence that shows that this is the same as A intersection B complement unioned with, I should put parentheses there, B intersection and the A complement. I think it's actually much more intuitive just to say exclusive or even symmetric difference. But when you're doing algebraic set manipulation, sometimes you need to take that XOR into the minuses and then take the minuses to the intersections. So now we have something that we can manipulate, right? So we can, apply to Morgan's law if we want to negate it, or commutative law, we can do things with it now. Whereas when we're using the minus notation or the XOR notation, we can't do anything with that. So that's the main reasoning behind these new notations. Okay, the other thing that I would like to show you are a couple of algebraic rules that we had before that were not listed in the algebraic rules for the set theory chapter. But they're still true. I haven't figured out yet if that was a mistake on the part of the authors, or if there's a different reasoning behind them, so they would require a separate explanation. They just didn't do it. But we can still use those rules, and those are the bound rules and the negation rule. So, if you recall, the bound rule, P and 0 equals 0. P and 1 equals P, right? So if P is 1, the result will be 1. If P is 0, the result will be 0. And P or 0 equals P, and P or 1 equals 1. Doesn't matter what P is, the output's 1. So that's our bound rule. Do we have the same thing with set theory? Yes, right? What is the equivalent of 0 for set theory? It is the empty set, right? It is a set with no members. What is the equivalent of 1 with set theory? That is our universal set, with my fancy U there, right? The universal set is everything. So let's kind of do a real example here. Let's say that we have a set S and it consists of 1, 2, and 3, because I am not creative. If we have S intersection, which is the same as and, the empty set, what's that going to be? Well, S has nothing in common with the empty set because there's nothing in the empty set. So the result is going to be the empty set. If we have S union the empty set, what are we going to get? We're going to get, our original 1, 2, and 3. Nothing is contributed from the empty set because it has nothing to contribute. So the result is S again. Oh, and I kind of flip these around. By the same token, if I have S intersection with the universal set, well, the universal set contains everything, including everything that's in S. If the only things that count are what's in both S and the universal set, that's going to be, by definition, S. If I have S unioned with the universal set, well, it doesn't really, everything that's in S is in the universal set because S is a subset of the universal set. So the result must be the universal set. So those are our bound rules. You can see how this directly relates to the bound rules that we used with predicate and propositional logic. And just to make it a little bit clearer, so those are bound rules. Let's take a look at the negation rules. If you recall the negation rules, P and not P, which technically should be in parentheses, equals 0. The other rule is P or not P equals 1. Both of which are pretty intuitive, right? If we go back to the first one, P is 1 or 0, not P is 1 or 0 is the opposite. If we AND them together, we will always get 0. By the same token, if we OR them together, one of them has to be 1, right? So if we use our same set S of 1, 2, and 3, and we're going to, now notice now we no longer have the empty set and the universal set being explicitly stated, but they're still there. If S is 1, 2, and 3, then what is S complement, right? Remember, S complement is the same as not S. So what is contained in not S? It is everything that's in that universal set except for 1, 2, and 3. Everything else is a part of S complement. So knowing that, if we have S intersection with S complement, well, since everything that's in S complement, since S complement is everything that's not in S, and S is everything that's not in S complement, then by definition, their intersection is going to be the empty set. By the same token, if we have S unioned with S complement, well, we've just shown right here that S complement is the universal set minus S. So once we union them back together, we get the universal set. So our negation rules and our bound rules still apply. They are just a little bit different because instead of zeros and ones, we're talking about the empty set and the universal set. Okay, one last bit of terminology that I want to kind of impart to you is you might see something that looks like this, right? So X and Y are each members of A and B, right? So this is the Cartesian product, and it means X is a member of A and Y is a member of B. Now, when you're doing, graphing and you have your little kind of chart and you do X, Y here, let's say that's 3, 5. In that case, A is the set of integers and B is the set of integers. So they're the same, so it's pretty simple. More commonly with what we're going to be doing, A and B are different sets entirely. So A might be A, B, C, and B might be 1, 2, right? So they're two totally separate sets. And when I say xy is a member of A comma B, what I mean is xy is a tuple with some value from A and some, so for example, it could be A2 or it could be C1 or any of those combinations. And later on in this chapter, we're going to talk about how we calculate how many combinations there are. But for right now, I just want you to understand the terminology of a Cartesian product. And it doesn't have to be a tuple. It can be a 3-tuple or 4-tuple. So you can have as many sets as you want to form this product. Okay, so that is everything that you need to know that wasn't covered in the first 2 videos. That's going to come up in the rest of the sets chapter. If you have any questions, ask in the forum below.